From their birth to their eventual deaths, stars are in a constant battle, a battle which they will inevitably lose. At first, the star calmly fights against the pull of gravity by fusing light elements into slightly heavier elements. When they run out of hydrogen and begin to collapse in onto themselves, they panic and begin fusing heavier and heavier elements within their cores, constantly fighting against their own weight. This process continues until the only thing left to fuse is iron. This is the end of the road for the star, as the iron will not provide any useful energy for outward pressure. The entire mass of the star begins to accelerate towards the core, pulled in by gravity, with nothing left to resist this weak and persistent force. This part of a star's life was covered in depth in the last star classification video I made, and I'd recommend checking it out before watching this video. Once the dust has settled, and you peer behind the matter flying away from the star, assuming this was a lower mass supergiant star, a neutron star will be left behind. Neutron stars are the smallest and densest stellar objects in the universe. The only objects denser than a neutron star that are confirmed to exist are black holes, which we will cover later. These stars are no more than 20 kilometers across, which is no wider than an average sized city. You can think of these stars as a compressed white dwarf or a gigantic neutron. The gravitational collapse has compressed the atoms so that the protons and electrons combine to form electrically neutral neutrons. To get an idea of how dense that is, a single tablespoon of a neutron star could weigh about 900 billion kilograms on Earth. This is massive enough for you to feel its gravitational pull standing right beside it. And if you got too close, you'd be torn apart by the severe gradient of the gravitational pull, or the tidal forces. A full-sized neutron star can be many times more massive than our Sun, despite only being 20 kilometers in diameter. Meanwhile, our Sun's diameter is somewhere in and around the 1.4 million kilometer region. The only thing preventing further collapse in a neutron star is the neutron degeneracy pressure, as described by the Pauli exclusion principle, where two of the same fermions cannot occupy the same quantum state within a quantum system simultaneously. I briefly touched on this in the brown dwarf and main sequence star videos, in which I mentioned that white dwarf stars are kept from further compression by electron degeneracy pressure. Now, if any more mass is added to the neutron star, the neutron degeneracy pressure and other nuclear forces would not be sufficient to prevent the star from further collapsing into a black hole. So it only takes a little push to turn that neutron star into something much, much scarier. Remember the surface temperatures of main sequence and giant stars, and how they rarely ever exceeded 30,000 Kelvin? Well, the surface temperatures of a neutron star could be as high as 600,000 Kelvin, and that's quite a high surface temperature for such a tiny object. A pulsar is a rotating neutron star that emits beams of electromagnetic radiation out of its magnetic poles. When this beam is briefly directed at Earth, we can detect it, and we can find out how fast the pulsar rotates. Due to the conservation of angular momentum, when a rotating supergiant star collapses into a tiny neutron star with only a tiny fraction of the diameter of the original star, the rotation speeds can be absolutely mind-boggling. In order to help you imagine the rotation speeds of some pulsars, I'm going to play a couple of sounds of electromagnetic beams that have been converted into these audio signals, originating from different pulsars rotating at different speeds. The thumping noises you hear are the sounds of the beam passing Earth once. Basically, the star rotates 360 degrees after every two separate thump noises. But some pulsars rotate so quickly that all you can hear is a loud, high-pitched or buzzing noise. I'd recommend turning your volume down for this one. Well, that was quite something, wasn't it? If you've listened closely, you may have noticed that there is a slight difference in rotation speeds of these objects. The slowest pulsars rotate about once per second. The fastest, which are called millisecond pulsars, as you could hear, spin so fast that they sound like one continuous audio signal. The fastest spinning pulsar rotates at about 700 times per second, or with a frequency of 700 Hz. Now this must be a spectacular sight, an object with a mass magnitudes higher than our Sun's, about the diameter of a city, rotating at those speeds. Now that's not something we can really imagine properly. Quark stars and strange stars are hypothetical and have not actually been observed yet. However, their existence is theoretically possible, and they are objects of mystery and great intrigue. A quark star is a potential middle stage between neutron stars and black holes. A star dense enough for its core to consist of free quarks. Quarks are fundamental particles, if you didn't know, which combine to form other compound particles such as neutrons and protons. A proton is made up of two quarks, one up and one down quark. If the degeneracy pressure keeping a neutron star from collapsing is overcome, this could be the next step preceding the collapse into a black hole, a final stand against gravity, if you will. The pressure in these hypothetical stars would be so great that the neutrons would dissolve into the quarks that they were made up of. These objects definitely have the potential to exist somewhere out there, almost indistinguishable from regular neutron stars, and perhaps even harder to locate because of their slightly different electromagnetic fields and surface temperatures. Now, I'd like to build on this idea of a quark star with a strange star. A strange star, or a strange quark star, is another hypothetical star that is directly related to the quark star. They're basically the same thing. It's basically a neutron star which, at its core, is made up of strange quarks. A truly bizarre state of matter. And this quark is the only type of quark that could really remain stable at the insane pressures inside the core of a quark star. So these stars could exist, although they're quite difficult to detect and prove. Now, strange matter really does live up to its name in a very unique way. Strange matter has a tendency to turn everything else it comes in contact with into strange matter also, in a similar fashion to fire spreading, or a disease spreading. This strange matter has the mind-blowing potential to infect the entire universe, believe it or not. If two of these strange neutron stars collided, and sent the strange matter flying out in all directions, and that strange matter came into contact with another object in space, such as a planet, it might have the potential to immediately infect the planet and turn it into a lump of strange quarks. This is because strange matter is the most stable state of matter possible, and all neutrons and protons that come into contact with it immediately dissolve into it, and they lower their energy states. And that's sort of the simplified version of it. Luckily for us, this type of matter has never been directly detected anywhere near Earth, and even if some strange matter did exist on Earth's surface, it most likely won't consume it, because strange matter is thought to be positively charged, just like the Earth's surface, and it will therefore repel the Earth's surface. As you know, like charges repel and opposite charges attract. However, if negatively charged matter starts making its way to our planet, it would be a good time to pack our bags and head out. But luckily there's no evidence of this negatively charged strange matter being anywhere near Earth, or even existing in the universe. So I guess that's good news for now. Black holes aren't stars, so it almost feels wrong to include them in this series, but they are usually related to the death of a supergiant star, so we'll briefly go over some black hole characteristics. Black holes are the densest objects in the universe, with the mass of the collapsed star that they're made up of being compressed into an infinitely small point known as a singularity. The sheer density of the singularity means that it creates a region around itself, a dark sphere that nothing can escape from, known as the event horizon. The second any matter or energy crosses this event horizon, it can't exit the black hole again, as all paths will lead straight towards the singularity. This means that light itself cannot escape the black hole, and in order to escape, you'd have to travel faster than light and reverse time, turning the black hole into a white hole, which is pretty much impossible. Now, what I just described there was a Schwarzschild black hole, or a stationary and chargeless black hole. This isn't really a black hole you'd find out in the wild. If you fell into this black hole, you'd be spaghettified and torn apart by the tidal forces of the black hole, and your atoms would travel towards the singularity, and that would be the end of you. But, as we have learned from the neutron stars, chances are black holes in the wild aren't going to be stationary or chargeless. So then, how do rotating and charged black holes behave? Let's start with the rotating, or the Kerr black hole. It's the kind of black hole you're likely to come across in our universe, as the stars they've collapsed from were also rotating. So these bad boys are probably rotating pretty fast. These black holes usually appear to have light orbiting them as well, known as photon spheres. And these photon spheres are the reason we can actually see these black holes using visible light, like we did when we took that picture back in 2019 of that famous black hole at the center of a nearby galaxy, known as M87. Now, these black holes bend and distort space so that you can see the stars behind the black hole from the other side. The bizarre distortion of these photon spheres can be attributed to the gravitational forces of the black hole. Matter and even planets can orbit these black holes, but the closer they are to the event horizon, the faster they have to be traveling through space in order to resist the flow of time into the black hole, otherwise known as gravity. Oh, and there is this one thing I forgot to mention, and it applies to all objects with mass and a gravitational pull, but this effect is exaggerated near objects like neutron stars and black holes. Gravity doesn't just distort space, it distorts space-time. An example of this effect is a fast-moving satellite orbiting Earth at around 10,000 kilometers. It experiences a slightly weaker gravitational pull, so time moves faster for it than it does for us. However, speed also changes how you experience time. The faster you travel, the slower you appear to move through time to an outside observer that is stationary in space. You can think of it like this. Everything in the universe is traveling at the constant, c, the speed of light. The faster you travel through space, the slower you'll appear to travel through time. If you're floating in space, in the middle of nowhere, completely stationary, you'd be moving at full speed through time. On the other hand, if you're a massless electromagnetic wave, like visible light, or if you're a massless particle, like a photon, you'd be traveling at full speed through space, and at no speed through time. This is why light doesn't experience time at all. And if you were to travel at the speed of light, which is impossible because nothing with mass can travel at the speed of light, but if you could, then you wouldn't be able to experience any time passing. You would just exist. Now, this relativistic time dilation isn't really time itself moving at different rates for objects traveling at different speeds or influenced by different gravitational forces. It's more a matter of perspective. The best way I can explain it is, if you look at an object traveling towards you head on, they appear to be squashed. They look shorter than they actually are. Let's just say a car is traveling towards you. It looks as if it was shorter, but it's not actually shorter, it's just traveling towards you. It's your perspective that makes the car look shorter, but the car is actually the same length. A similar effect happens with objects traveling through space at a different speed than you're traveling through space. Essentially, they're traveling at a different angle than you are through time. Their time looks squashed. It appears to be more compressed than your time. Or the opposite could be true. Their time could appear to be longer than your time. But that's just a matter of perspective. It just depends on your own speed through space. But that's a topic for another video, and I'm sure there's other people out there that have covered that topic much better than I ever could. Now, this same effect that I've described can be applied to a black hole and any object with a strong gravitational pull. As you near the event horizon, time will appear to move at a normal rate for you, but from an outside observer watching you fall towards the event horizon, you'll appear to slow down. Your movement through time for them is slower. This isn't because time is actually moving more slowly for you, it's the perspective of the observer, which is traveling at a different angle through space-time. As you cross through the event horizon, from the observer's point of view, you have frozen, and you begin to redshift slowly until you disappear. At this point, billions of years have passed, and from your perspective, the entire universe outside the black hole seems to have sped up. The universe shrinks into a bubble behind you as you continue falling towards the singularity in this spinning black hole. But something's different, because as we've mentioned before, this is a Kerr, or rotating black hole, and not a Schwarzschild black hole. And because of this spin, the singularity isn't actually a singular point, but has instead been drawn out into a ring with no thickness. This ringularity has another event horizon. That's right, an event horizon within an event horizon. You can avoid spaghettification and brutal death, at least for now. It's theoretically possible to use this black hole as a wormhole to a different universe. You can never go back to the universe you came from, no matter how fast you go or what direction you go in, but you could potentially travel onwards towards another universe in your future, unlike a Schwarzschild black hole where all your future world lines go towards the singularity. However, due to more complex reasons involving opposing charges within the black hole, you might not ever make it through the singularity without being obliterated. Sadly, this universe was just not made to be our playground. It sucks. But there are other types of black hole, like the Reisner-Nordstrom and the Kerr-Newman, and the latter is a static charged black hole, and the former is a rotating charged black hole. These share a lot of characteristics with the previous two categories of black hole, and each one is more or less the same as the uncharged variant in terms of behavior. Now, there is something you need to know about the singularity of a black hole. There is this concept in physics of a naked singularity, and it kind of scares physicists a little bit. A naked singularity is basically a singularity that has no more event horizon. And this type of singularity is theoretically possible. For example, if you take a rotating black hole and you continue to make it spin faster and faster and faster, it may eventually reach a point where the inner event horizon actually meets the outer event horizon and they cancel out, and you get a naked singularity. Now, nobody actually knows if this is actually possible, or if there's some sort of deeper physical reasons for these naked singularities not being possible. But deep down, I kind of wish naked singularities are possible, because, come on, who doesn't want to see a naked singularity? Rule 34 applies. Anyway, this is the end of the video. Thanks for watching, and I regret to inform you that this is also the end of the star classification series. For now anyways, unless something completely new is discovered. But it's been quite a journey, and I appreciate all my viewers, all 10 of you guys. Good job hanging on in there till the end of the video. And yeah, don't forget to subscribe. You better subscribe.